So let's go over a very basic mechanism you'll see over and over again in biochemistry. Let's say we have this carboxyl group reacting with an alcohol. We know these two functionalities can react because we know this oxygen on this alcohol can act as a nucleophile, and we know these carbons and these carbonyls, these carbons can act as electrophiles. So we can have a reaction. This oxygen nucleophilically attacks this carbon. When it attacks, it pushes these pi electrons up onto this oxygen. When we do that, we've essentially formed a bond represented by this bond, and then we push these pi electrons up onto this oxygen, creating this oxygen anionic tetrahedral intermediate. Then at some point, this hydrogen would have gotten deprotonated, but we'd form this intermediate. Then once we form this intermediate, we know the electrons can scooch back down. When they fall back down, they form a double bond. And when that double bond is formed, now we'd break this bond with these electrons falling on this guy. And if we did that, remember the electrons fall back down, forming a double bond represented by this double bond. And then this bond is broken, and this guy floats away as this leaving group. So now we form our product. So now we've had the reaction. But realize, this is a terrible leaving group. This hydroxide is not stable. This is a terrible leaving group. This hydroxyl was a terrible leaving group. So really, in reality, this reaction isn't really feasible. This reaction will occur very minorly because, again, this is such a poor leaving group. So we don't want to break this bond forming this leaving group because this is an unstable leaving group. So in reality, this reaction wouldn't really occur, or it would occur very little. However, what if the cell needs to do this reaction? Maybe we need a reactant alcohol with the carboxyl group to form this product. Maybe for whatever reason the cell needs to go through this reaction. How can we do this if this reaction isn't feasible because we have such a poor leaving group? Well, we can use the energy in ATP. So the way we do this is, again, we want these to react, forming this product. So what we can do is we can take this carboxyl group and we can activate it. We can activate it. So again, we take it and we're essentially activating it. And the way we activate it is we react it with this ATP. We use this ATP to activate this carboxyl group. So how would we do this? Well, again, we know this oxygen can act as a nucleophile. Its lone pairs of electrons can act as a nucleophile. And we know this phosphorus is electrophilic. It has all these bonds to these very electronegative oxygen atoms, which pull and steal a lot of electron density. So as they steal electron density, we have an electrophilic phosphorus. So now we have an electrophile and a nucleophile, so now they can react. The oxygen nucleophilically attacks the phosphorus. When we attack, we push these pi electrons up onto this oxygen. So when we would do that, we'd essentially form this intermediate. Because again, we attacked, so we formed a bond represented by this bond. Once we did that, we pushed these pi electrons up onto this oxygen, creating this oxygen anionic trigonal bipyramidal intermediate. So this kind of trigonal bipyramidal intermediate you should be familiar with, but again, we attacked forming this oxygen anionic intermediate. Now, once we form this intermediate, and again, this would have gotten deprotonated, this hydrogen got deprotonated, but now the electrons will fall back down. When they fall back down, they form a double bond. When that double bond is formed, we break this bond with these electrons falling on this guy. When we do that, we'd essentially form this product, where again the electrons fell back down, forming a double bond represented by this double bond. Then we break this bond, so this bond's broken. So that bond was broken. And then again we have these two guys, which I'm just rearranging them. But so essentially we've broken this bond, and now this group, which again was ADP, will just float away. So we've done it. We've activated this carboxyl group. We've essentially, using the energy in ATP, we've activated this carboxyl group. So now we have this activated carboxyl group, and now it's ready to react with this alcohol. Now we can go through the same mechanism. Nucleophilically attack. When we attack, we push these pi electrons up onto this oxygen. Again, when we do that, we know we form this oxygen anionic tetrahedral intermediate. But now, look what we can do. The electrons can fall back down. When they fall back down, they form a double bond. When that double bond is formed, now we break this bond. These electrons fall on this guy, and we can't do that because this is a good leaving group. Remember, when we didn't activate the carboxyl group and when we had this tetrahedral intermediate step, we couldn't break this bond. We couldn't break this bond because this was a bad leaving group. But now, instead, we do have a good leaving group. Now we do have this good leaving group because we activated this carboxyl group with this ATP. So now we do have a good leaving group. So now we can break this bond. Now this is feasible. We've created a better leaving group. Now the electrons can fall down, forming that double bond, breaking this bond. This bond is broken, these electrons fall on this guy, and we'd essentially form these products. So ignore this for now, but essentially we'd form this product where again the electrons fell down, forming that double bond, represented by that double bond, and then we broke this bond. We broke this bond, this guy floats away as this guy, and we've done it. So now we've had the bond, we've done the reaction. We had these two compounds, and we wanted to form this product, so we've done it. And we've made it in a feasible manner because essentially the point is we use this ATP to create a better leaving group. So now that we've created this better leaving group, we can allow this reaction to occur. So essentially we use this energy in ATP, this high energy state, to essentially activate this carboxyl group. So now we've activated it. So now we do have a better leaving group. And now that we have a better leaving group, we can have this reaction occur. So that's one of the ways we use ATP, and essentially in any of my videos, on my videos on enzymes or biochemistry videos, whenever you see a reaction where we had a bad leaving group, I did a reaction with the bad leaving group, really what would happen is we would create a better leaving group using ATP. Once we've created that better leaving group, now we can go through the exact same mechanism, but essentially now we have a better leaving group, so now we've made the reaction feasible. So essentially that's what ATP does. And there are different ways ATP can fuel reactions, but one way is we use the ATP to create better leaving groups to allow reactions to occur. And the way I like to think about this thermodynamically is, again, we had that reaction. We had that alcohol reacting with essentially this free fatty acid, this carboxyl group, and they react and they form these products. And we said this reaction wasn't very feasible. It was essentially the equilibrium constant and essentially wouldn't allow this reaction to occur very much. Because again, we created this very bad leaving group, so this reaction wouldn't occur very much, and it would have a very low equilibrium constant. However, we know ATP hydrolyzing is very thermodynamically favorable, and it would have a very large equilibrium constant. This reaction is very, very favorable. So essentially what we can do is we can use the favorability in this equilibrium of this reaction, hydrolyzing this ATP, we can use this favorability to push this reaction forward. So we're using, even though this reaction has a low equilibrium constant and isn't very favorable, we can couple it with this ATP reaction, which is very favorable, to push this reaction forward. And the way I like to think about it is, again, we use this, again, we can kind of put these two reactions together. Where, again, remember our reaction, we essentially activate this free fatty acid by reacting it with ATP, forming this product. And again, remember, this reaction is very favorable. Hydrolyzing that ATP, forming these products, is very favorable. So this reaction is very favorable. We are essentially breaking that ATP bond. So this reaction is very favorable. So because this reaction is so favorable, strongly going in this direction, we're creating a lot of this guy. This reaction's favorable, so we're creating a lot of this guy. So now that we have a lot of this guy, essentially we've created a lot of this guy, so we have high amounts of this guy. We can react it with this guy, and which pushes the reaction forward. So now we can push the reaction forward, and now we can create our products. And again, it's the same idea. So we've created our same product. We just used essentially the equilibrium of this reaction, pushing this reaction forward. We use the favorability of this equilibrium of this reaction to push this reaction forward, and that's what's going on. So again, originally this reaction had its own equilibrium constant, but once we've added it with this reaction's equilibrium constant, we've essentially created a new reaction with a new equilibrium constant. And again, you could also think about it in terms of delta G's, of exergonic thermodynamic favorability. So again, maybe this reaction wasn't very favorable, but this reaction was very favorable. So we can use the favorability in this reaction to push this unfavorable reaction forward. And again, we know delta G's are additive. So if this was a very positive delta G that wasn't favorable, but this was a very negative delta G that was favorable, this reaction together, you add these together and you can see the overall delta G of the reaction. And again, when it comes to equilibrium constants are multiplicative. You multiply equilibrium constant. So if this reaction had its own equilibrium constant and this reaction had its own equilibrium constant, you can essentially multiply these two equilibrium constants to find the equilibrium of the new reaction. Equilibrium is multiplicative.